My semester project is optimizing MobileNet V2 for drone identification of military targets. It was inspired by the Russian invasion of Ukraine, where small, low-flying drones are being used by both sides in the conflict. Small drones equipped with cameras are quite common today and can be used for object identification. What's critical in this application is being able to distinguish between military targets and civilian non-targets. The datasets used in this project include military targets, buses, trucks, vans, cars, construction vehicles, and farm equipment. It is quite easy to identify the objects in the previous images, but it's much more challenging to identify a military object when it's camouflaged, or a civilian object when it is obstructed by trees or other vegetation. Since no datasets were available with camouflage or tree-obstructed views, a dataset was created for this project. Each image was sliced into 12 pieces, and those 12 pieces were combined with a random forest image. Where the two images overlap, the pixel intensity is 50% from each image. Where there's no overlap, it's 100% of the forest image. The same process of sectioning and combining with a random forest image was followed for civilian objects as well. The total dataset used for this project ended up being 24.8K civilian non-target images and 12.8K military target images. The baseline model for this project is MobileNet V2 using transfer learning with initial weights from ImageNet. The top was removed and two dense layers were added to get to the binary classification. In addition, a custom loss function was developed to minimize false positives, where a civilian non-target is identified as a military target. The model was developed on Colab, but embedded systems have restricted memory and processing power, so post-training quantization and clustering were applied. As you can see in the table, there's almost no effect on performance because of quantization and clustering. You see that in the accuracy and the number of false positives. This test set was quite large, but when 1,000 test images were used on the Coral Dev board, they were able to complete that inference in 45.9 seconds, which is about 21 images per second. In an effort to improve accuracy and reduce the number of false positives, an object detector was developed for finding regions of interest. As you can see on the right, non-maximum suppression was used to reduce the number of regions of interest that the model had to consider. When using regions of interest, if any region includes a military target, as predicted by the model, then the image is considered to have a military target. Only if all regions of interest are predicted to not have a military target can the image be considered to be a civilian non-target. Unfortunately, what can be seen here is that MobileNet V2 performed very poorly, and that is very likely to the fact that it was trained on full images and not on regions of interest. Two additional models were developed for comparison with the fine-tuned MobileNet V2 model. This is the simple model, which consists mostly of a number of convolutional layers. As you can see, the accuracy was reasonable, about 2.5% different from the MobileNet V2 model, but unfortunately, the number of false positives was extremely high, about 58% more than the MobileNet V2 model. As mentioned earlier, the fine-tuned MobileNet V2 model do not do well with regions of interest. Simultaneous classification and object detection is addressed with the YOLO V4 model. In order to add the military target class to the COCO dataset via transfer learning, a small number of military target images were annotated with bounding boxes. As you see in the table, accuracy is quite high, within 1.5% of the fine-tuned MobileNet V2 model. Note that as only the military target class was added, there's no confusion matrix and no ability to check false positives, only false negatives. Although not tested, the expectation is that the YOLO V4 model would provide inferences faster on an embedded system, allowing a trade-off between the accuracy of the fine-tuned MobileNet V2 model and the speed of the YOLO V4 model. Some key takeaways. MobileNet V2 provides highly accurate predictions of military and civilian images on the custom dataset. YOLO V4 predictions are not as accurate, although YOLO V4 holds the promise of faster inferencing. To test the true value of the model developed, real images or video of military and civilian objects is required.